Hello, my name is Corey Martin, and I just recently finished my third year working with Dr. Natalia Shestova at the University of South Carolina. My primary area of research is focused on understanding the dynamic behavior of photochromic metal organic frameworks or MOFs, specifically on the control of electronic properties and the photophysics of photochromic frameworks. MOFs are a class of materials that are constructed by combining inorganic secondary building units, or SBUs, and organic linkers to provide scaffolds that are crystalline, robust, permanently porous, and most importantly, modular. These precedents for MOF design provide a highly tunable platform to advance the growing technological sector by their potential application in heterogeneous gas phase catalysis, high volume but low pressure gas sorption, atomically precise molecular sensing, and much more recently as semiconducting device components. Although an impressive set of applications have already been realized for MOFs, by incorporation of photochromic molecules, we can expand this library at the flick of a switch by providing light-based control of their intrinsic properties. In my presentation today, I will highlight MOFs that we have made in the Shestova lab constructed of two-dimensional layers of photoinactive tetracarboxyphenyl dibromobenzene and zinc paddle wheel inorganic secondary building units, in which the layers are pillared together by photochromic linkers. This presentation will focus on two of the many photoswitches that we are working with in the Shestova lab, being the pyridyl-terminated spiroporine and the pyridyl-terminated diarylathane photoswitches. As an initial method to study the photoisomerization process of photochromic MOFs, we performed time-resolved diffuse reflectance measurements where we would photoisomerize our MOF under UV exposure and then measure the attenuation of the photoswitch over time. We were able to fit this data with first-order rate kinetics in order to extrapolate rate constants associated with these changes, as well as optically monitor the changes in photoisomerization as a function of UV and visible excitations. With these MOFs, as well as others, we have studied the electronic properties through pressed pellet and single crystal conductivity measurements, which each have their own advantages and disadvantages, as well as probing the electronic structure through measuring the density of electronic states nearest to the Fermi level using X-ray photoelectron spectroscopy, and modeling this as well as the electronic band gap using theoretical calculations. As a next step, we wanted to correlate the changes observed in optical data with the changes in electronic behavior. We did this by performing diffuse reflectance as well as pressed pellet and single crystal cycling measurements, where we would apply a steady voltage and measure the current over time as a function of UV and visible excitations. Indeed, the rate of attenuation corresponding to that of the optical studies corresponded for both of our diarylathane and spiroporine containing MOFs. After completing these studies, we applied our understandings to develop a single transistor amplified LED circuit where a MOF was wired into the base of the transistor in order to toggle an LED by UV excitation of our photochromic MOF. And with that, I want to thank my advisor, Dr. Natalia Shestova, as well as my group mates and alumni, our collaborators, our funding, and of course all of my undergrads who are invaluable for all of their hard work. And thank you for listening to my presentation.